So yesterday, this is where we got to, and I was just telling you how to build a nuclear bomb. I think that's where we got to, right? Okay. All right. So I told you how the fuel cell, or how the fuel rods work in the nuclear reactor. Okay. But in a nuclear bomb, okay, what they do to cause these atoms to split, okay, is they surround them with a casing of high explosive, usually like C4, okay, or you know, thermite or something like that, okay, and they'll surround it, and they'll have this piece or chunk of uranium, or usually it's plutonium, because it's a little more volatile, okay, in the middle. When you detonate the high explosive on the outside, all the particles, okay, the atoms and everything from that explosion are focused inwards at this chunk of fissionable material. All right, and what they will do is they'll start breaking some of those individual atoms. And when those atoms start to break, their pieces move off at high speed and hit other uranium atoms or plutonium atoms and break them. All right, and then it becomes a chain reaction that feeds itself, and eventually, kaboom. Okay, and you get this big nuclear explosion, okay, that releases lots and lots of energy. All right, the key point of this was all to say that yes, the particles are essentially in nature indivisible. Right? But if you have the proper technology and the know-how, they are divisible. Right? Are they still going to retain the same properties after they've been divided? No. All right? Because now they have different numbers of protons, neutrons, whatever. Okay? They're different things now. You've got a whole bunch of different materials because you've actually physically changed the structure of the atom by taking it apart. All right? Okay, second point. Atoms of the same element are identical. All right, really important that we understand that. If you had a lineup that you could actually see of a bunch of oxygen atoms in a row, you would not be able to tell any of them apart because they would be absolutely 100% identical. All right, they would all have the same number of protons, they would all have the same number of neutrons, same number of electrons. There'd be absolutely no way to tell them apart. And that is why every atom of oxygen has exactly the same physical, chemical properties. Okay? The properties of a material are based on the structure of its particles. Okay? Whether those are atoms or molecules, depending on what they are. Okay? But that's what determines the properties of that material. So oxygen is a gas at room temperature. Okay? It has a certain density. You know, it reacts. It's very volatile. It reacts with all kinds of things. That's what fire is. Okay? It's a reaction with oxygen. So those are its properties. Whereas if you looked at an atom of iron, okay, it would have considerably different properties because it has a different number of protons, neutrons, and electrons, making it a solid, a metallic solid at room temperature, you know, that is attracted to magnets and things like that. All right, so the structure of the atom determines the properties. So atoms of the same element are identical. Atoms of any one element, okay, are different from those of any other element, and that's why we have all of these different materials. Okay. Third point, atoms of different elements can combine with one another in simple whole number ratios. Really important that we know that it's always whole numbers. You never have half an atom in a compound. Okay? It's always a whole atom. All right? Like if we look at the formula for water, right? It's H2O. How many hydrogens? How many oxygens? One, right? It's never written like this. Because what's half an oxygen atom? Good, there isn't an answer. I don't know what it is either. I don't know how you have half of an oxygen atom. Okay, it's got an odd number of particles in it. I don't know. What's that? Oh, absolutely, yeah. Yeah, guys, if you want to follow along on your phone in the notes, go right ahead. I told you yesterday that's just fine with me. All right, so everyone understands what we mean here. Simple whole number ratios. You're never going to have less than a whole atom when they group together. All right, so they can go together and make compounds. Right, you could have H2O, you could have NH3, okay, which is ammonia. You know, you could have any number of things, any number of compounds. Okay, even more complex things like, you know, C8, H18, or C6, H12O6, okay, which is glucose. They're always whole numbers. They're never going to be halves, okay, 3/4 or anything like that. All right, fourth point is probably the most important point in terms of understanding why chemical changes occur. Okay, so chemical reactions occur when atoms are separated, joined, or rearranged. Now, when we say atoms are separated, we don't mean pulling apart a single atom. We mean pulling apart a molecule, taking this atom and pulling them apart. Okay? Splitting an atom isn't pulling it apart. All right? So chemical reactions occur when they are separated, when they are joined, or when they are rearranged. So as an example, if I had this material and let's say oxygen reacting with each other, okay, I would be rearranging what happens. Okay, I'd be rearranging the materials I have. All right, this is the reaction that occurs in the engine of your car. This stuff is called octane. Right, it's the stuff, the active ingredient in gasoline. Right, oxygen gas, and you always end up with these two things. Okay, is there anything new on the other side of that arrow? There are some new substances. Okay, there's new compounds. There's carbon dioxide and there's water, whereas on this side there was, octane and oxygen. But are there any new elements over there? No. Okay, a chemical reaction cannot produce new elements. You only can ever have what you started with. This was the thing that showed the alchemists could never do what they wanted to do. Right? They wanted to transmute this thing into that thing, and you can't do that. I can't make lead turn into gold. Right? I can turn these two things into something else, okay, but I can only ever have the stuff they were made of end up over here. Does that make sense to everyone? All right, so that was sort of the death of alchemy right there. Okay, was when Dalton realized every chemical reaction I do, I always end up with only what I started with. Maybe in a different order, maybe with different properties, but I never create any new elements from this chemical reaction. All right, so does that make sense to everybody? Okay, we can't create any new elements. We can create new materials, certainly, but we're not going to do the thing the alchemists thought that they would be able to do. All right, so this would be a rearrangement reaction. Okay, we could be joining elements together. Okay, that's called a synthesis reaction, which we'll get to later. If I had hydrogen and oxygen, all right, I would be able to produce H2O, right? Okay, might be able to do that. Okay, I could separate them. Okay, the process for making rocket fuel is the exact opposite of this reaction. The electrolysis of water. You force a high current through water, and it'll separate back into those two things. All right, I've separated hydrogen and oxygen now. Do I have anything other than hydrogen and oxygen? Nope. Okay, still have what I started with, but I make it look different. Okay, and that was unfortunately what the alchemists didn't understand, right? They were like, well, when I mix these two things together, look what I get. It's nothing like what I started with. But they didn't understand that it's still made up of the same stuff. Sure, it looks different. Maybe it started on fire, whatever, but it's still the same stuff you had. All right? Even a campfire, right? When you have a campfire, you start out with wood and oxygen gas. And what do you have when you're done? Well, you have fire, but at the end you have ash and smoke. Well, what's in the smoke? Hydrogen, oxygen, carbon dioxide, right? Like you've got essentially water vapor, carbon dioxide, but it's all the same stuff you started with. Because what's wood made out of? Carbon, hydrogen, oxygen. Okay, so it's all there. Right. Okay, questions on that one? All right. So when Dalton was realizing how all of this kind of happened, he said, I need to be able to represent atoms with something, tell people what they look like. All right? Now, at the time Dalton was doing all of this, nobody knew about electrons, nobody knew about protons or neutrons, but now that they could see, or they could understand, sorry, that when a reaction happens, I still have the same stuff on the other side, the same elements that I started with, they were okay with saying, sure, this idea of the atom is okay. It does kind of make sense because we can see or visualize these atoms moving around and joining and rearranging and doing all this stuff. All right? So it made sense to say, well, the sphere is sort of the most common shape in the universe, right? The sun is a sphere and the moon's a sphere, the earth's a sphere. Just kind of a natural assumption to say they must look like balls. All right? So that's what the atom was originally thought to look like. Okay? Dalton's model was called the solid sphere. Okay? And that was fine. That was fine for the time. That's what people understood. It made sense to them. It fit with what their experiments were telling them. So people went along with it. Okay? Do we know different now? Yes. Okay, it would be impossible for a lot of the things we know to happen if atoms look like this. Okay. Okay, so shortly thereafter, one of these discoveries occurred. Okay, a guy named J.J. Thompson was doing experiments with what's called electrochemistry. Certain types of reactions will produce electric currents when they occur. All right, and he couldn't explain why a current would be produced in a reaction if atoms looked like a solid sphere. All right, because there was no explanation for where does that current come from. Okay, so what he said is maybe there's a part of the atom that's electrically charged, and in a reaction it can come off and it can go other places. Right? It seemed to fit with what his experiments were telling him. Okay? His experiments told him electric currents can be generated when a reaction occurs. He knew when a reaction occurs that atoms move around and rearrange, so it sort of made sense to say maybe part of that rearrangement is these little particles coming off and they'll travel through the wire and produce an electric current. Right? Since it produced an electric current, it made sense to call them electrons. Okay? So he said, I'll keep the solid sphere model, but I'm going to modify it to say that electrons are these small little negatively charged particles that are loosely embedded on the surface of the sphere. And they come off when a reaction happens. Okay. So this became the plum pudding model. I don't know why. I don't know what plum pudding looks like. I assume it looks something like that. Pudding with plums in it. Maybe it's like tapioca or something. I don't know. All right, but that's what he figured the atom must have looked like. And again, these were models that helped to explain or fit with the experimental results that people were getting. Okay, so that's why we're always changing the atom. The atom's always changing because we get new information, new data, and the old model doesn't fit. That's how science works. Okay, when one model doesn't fit anymore, it's modified. All right. Give you another example of that in science. It would be when your parents, okay, were in school. They were taught that all living things on Earth fit into how many kingdoms? 2. You were either a plant or you were an animal. Okay. Is that right? Not anymore. No. I mean, we know better, right? Because everyone just figured, well, mushrooms, they're not really a plant, but they grow like a plant, so we'll just put them in there. Right? When it was discovered that mushrooms actually are an organism that actually feeds on organic material, you couldn't call them a plant anymore because plants have to carry out what process? Photosynthesis. Fungus don't do that. Okay? So there had to be a new kingdom for all the fungi. Okay? They put them all in there. We had to change the way we classified things because we discovered new stuff. Okay? Similarly with single-celled organisms. They didn't really fit as plants or animals. Okay, so they had to have their own kingdom too, and then bacteria and viruses and all that, they had to have their own kingdom because they didn't fit in plants or animals either. So we had to modify what we were doing to fit with what we knew. Question? No? Okay. All right. Now, after the electrons were the idea of the electron came along, people said, well, if there's only electrons, then shouldn't the atom be negatively charged? There has to be something else there that balances off these negative charges. So the idea came along that there should probably be positively charged particles, okay, within the atom. All right. The big thing with that is, if there were only electrons and only protons, all matter was too heavy. Okay? There had to be something else in the atom that would make up more of the mass that seemed to be missing. Okay? Either protons were huge, or there was another particle in there that helped make up the remaining mass. All right? And so those were neutrons. There had to be a particle in there. They knew it didn't have a charge, so neutron, neutral. Okay? It sort of made sense there. And then for a while, there were all kinds of accepted models of the atom because nobody could agree on anything. Okay? Some still said, well, it could be a solid sphere with positive and negative parts and neutral parts and whatever, and we can do it that way, and that'll sort of make sense. Or no, it's maybe more like this, and the electrons kind of move around easily and float in space. People are like, well, how does something float in space? It doesn't really make sense. Shouldn't they be attracted to each other because they're opposites? And there was all this argument going on, and no one could really agree on what the atom looked like for quite a while. Okay? Now, the most important experiment in, let's say, modern physics / chemistry came along, okay, by this guy named Rutherford. Okay, what Rutherford did, okay, is he created an experiment with, and I think I have a picture of it here, like this, with this gold foil. Okay, he set up a source of particles, essentially like an X-ray machine. Okay, so it was shooting these X-rays at this piece of gold foil. Now, his argument was that if atoms are a solid sphere and they fit tightly together, all of the X-rays should bounce off of the foil and come straight back. Right? That would sort of make sense, right? Foil is solid, right? These X-rays, which are made up of really, really small alpha particles, should bounce straight back at me. But he said, I think that the atom is actually made of a very small, very dense nucleus surrounded by a cloud of very small, okay, electrons. Right? If that's the case, then most of the particles should go straight through the foil and hit the other side. Right? Now, what this thing here was made out of is photographic film. I know that you guys are kind of the generation where you've only ever had a digital camera, but cameras used to have this stuff called film in them. Okay? And when you would open the shutter, it would expose the film and the image would show up on the film. All right? So anytime this film was exposed to light, it would turn white. So he put this film around here. Since X-rays are a form of light, he shot the particles at the foil. And this is what happened. A lot of them got through, but they were deflected. Okay? Some of them bounced quite a ways, and some came straight back. Right? But the majority of them went through slightly deflected. Okay? So that said to Rutherford, I'm pretty much right here. The atom is made up of this nucleus, but the atom is actually mostly empty space. Right? It definitely isn't a solid sphere. Because if it was a solid sphere, all these particles would have come back at me. All right? He was very excited about it. He said it was like shooting a .50 caliber shell, okay, so like a big giant bullet, okay, at a piece of paper and having it bounce back. Okay, that's kind of what he said it was like. All right, it's a little dramatic, but okay, he had the electrons hitting the foil and essentially being scattered, proving that this is in fact what the atoms in that gold foil looked like. Sure, they're tightly packed from our perspective. From an atom's perspective, which is very small, there's a lot of empty space between where these X-rays could pass right through, okay? Or sometimes they would encounter a nucleus and be deflected. Everybody good with that? Okay, so that was the experiment that sort of proved that the structure of the atom was more like this. Okay, this was actually Rutherford's model. Okay, he believed that each electron had to have its own space, and these were just kind of separated by a few degrees, and they moved around like that, kind of set, and they were all about the same distance from the nucleus. All right. Now, we know that that's not necessarily the case, because a guy named Bohr came along, and he did some other experiments that proved that electrons can actually move around. Okay, they kind of orbit. There's different energy levels, and they can move from one energy level to the next. Okay, questions there? Okay, so Rutherford, right now, probably other than Dalton, your most important guy. Okay, he proved the nuclear model of the atom. Okay, so Niels Bohr. Okay, poor guy. Professor Boring was probably what he was called at university. Okay, had this idea that the electrons must orbit the nucleus like planets orbit the sun. Okay, the closer in they move, the faster they move. Okay, or they move more quickly because they have a smaller orbit. Okay, you get on the outside, they're getting further away. The ones on the outside could be easily lost, and that would help to explain Thompson's experiments of when a chemical reaction happens, sometimes an electric current is produced. So his model kind of explained a lot of the things that people were seeing. Okay. It also helped to explain something that another guy had found, which was that electrons can become excited when they get exposed to certain types of energy, right, or in certain situations. And when they get excited, they move faster and they can jump from one level to another. Okay? And then when they fall back down, they release that energy again. Right? How many of you have like a watch where if you've been out in the light for a while and then you go into the dark, parts of it glow? Okay, that's using this idea. Okay, what happens in a luminescent watch is that the electrons in that material that glows gain light energy. Okay, and they get excited and they move to higher levels. Then when you go in the dark and that energy isn't there anymore to hold them out further from the nucleus, they start giving up that energy and they release it as light. So as the electrons are moving back, they glow, and they only glow for maybe half an hour. Okay, something like that, before all the electrons have moved back to a low energy state and they stop glowing. All right, so that's kind of how that works. Okay, so Bohr's model was nice, but it was very rigid. Okay, Louis de Broglie decided, you know what, we need a less rigid model that more accurately shows that electrons can do this jumping. Okay, we call them quantum leaps. We'll talk about them later. Okay, moving from one energy level to another and do this quite easily. All right, so he decided, I've got to have a way to explain that isn't as rigid. So he came up with this cloud model, the electron cloud, and that's the one that's currently accepted because it does allow for this jumping and returning of the electrons. So electrons move almost randomly. Okay, and it's not truly random, but almost randomly throughout the area that is the atom. Okay, this is also how photosynthesis works. Okay, photosynthesis works on the same idea. When the sun hits the chlorophyll molecules, the electrons in the chlorophyll become excited and they move up to higher energy levels. And then when the dark reactions happen, okay, those electrons fall back down to their lower energy states, and the energy there is then used to make sugar. Okay. All right. Okay, so the structure of the atom as we currently understand is that there's dense, positively charged nucleus that has the neutrons and the electrons. That's the heaviest part. Okay, in fact, like 99% of the mass of all atoms is in the nucleus. Electrons are incredibly small. Okay, give you some idea. They are 9.11 times 10 to the minus 31 kilograms. Okay, so that would be what here? 1, 2, 3, 4, 5, 6, 7, 8, 30. I'm not going to do it. It's 30 zeros until you get to the 9. All right, so you got like decimal 30 zeros, 911. That's the mass, okay, of a single electron. It's incredibly small. All right, protons and neutrons are like on the order of thousands of times heavier than an electron, so they comprise almost all the mass. Okay. But as you can see, that does mean that an atom is mostly empty space. The sort of the border, or the edge of the atom, is the area where the furthest electrons or the highest energy electrons might still be found. Okay, so the atom isn't this thing that we can say, here's the edge of that atom. It's much fuzzier than that. Okay, it's kind of like the Earth's atmosphere isn't this rigid, perfect sphere. It has an irregular type of shape. Okay, so it's something like that. Okay, so all atoms are made of protons, neutrons, and electrons, and we've already talked about this. How can the atoms of one element be different from another? Well, it has to do with the number of protons, neutrons, and electrons. Okay, if you've looked at the periodic table before, all right, you can see that each element has a different number. Okay, so for example, hydrogen's number is 1. All right, that means it has how many protons? 1. Okay, it has 1 proton and it has 1 neutron, or sorry, it has 1 electron. How do I know it doesn't have any neutrons? I look at its mass. Okay, the mass of hydrogen is 1.00. Okay, 1.007. Okay, that means that if it's got 1 proton and 1 electron, essentially there isn't any other mass there. There can't be any neutrons. All right, you can calculate the number of neutrons in an atom, okay, by doing this, taking the mass and subtracting the atomic number. All right? So when you go 1.007 minus 1, what do you get? 0.007. Okay? If you can't get more than 1, there aren't any neutrons. Okay? So if we look at something like, let's say, lithium, okay? Lithium's atomic number is 3. Okay? So if we go, its atomic mass, which is 6.94 minus 3, okay, we're left with 3.94. How many neutrons do you suppose are in there? 4. Okay? Does that sort of make sense? You can always figure out how many neutrons there are by simply taking, so we'll just write that down maybe. Number of neutrons, okay, equals the atomic mass, okay, minus the atomic number. All right, you guys will be getting periodic tables, okay, from me probably next week. Okay, questions there? You good with that? Yep. Well, you don't actually weigh an atom. What we do is when we get to the mole, when we start talking about that, a mole is always represents the same number of atoms, and that's essentially what that mass is. That's the mass of a certain number of that many, or sorry, a certain number of hydrogen atoms, a certain number of oxygen atoms, et cetera, et cetera. Because you're right, you can't weigh one atom, you can't see it. You'd never be able to measure it because it's so small, right? Now, I'll get into when I teach you about the mole. I'll teach you about how they figured out what that number is and how they make sure they get that number when they do the measurements. But okay. All right. Now, I'm going to hand out to you some questions here that I'm going to want you to answer using the stuff from this lesson here. That when you're answering those questions, you answer in complete sentences that will be useful to you later. All right. All right, guys, so let's just go through these here real quick. If you're not done, don't worry about it. Well, you can just kind of copy along as we go here. So question number 1, idea of the atom was first proposed by whom? Democritus, okay, the Greek guy, okay, the Greek thinker. He wasn't widely accepted. For what reason? Aristotle. Yeah. Okay. They believed Aristotle. Aristotle's ideas made more sense. Okay. They were things that they could see and understand. Right. They saw that when you added fire to water, you got steam, and that made steam some parts air, some parts fire, and some parts water. It just made sense. Okay. His ideas were like, yeah, nice invisible particles. Okay. Yeah, go think of something else. Right. All right. Number 2. What elements did the Greeks believe all matter was made of? Well, we just gave them away. What are they? Right. Okay. Air, fire, water, and earth. Right. Why was that a logical conclusion? Yeah, it was something they had experience with, something they could understand. Okay. And that's what we always do. We always find the explanation that is most fitting to what we understand. Okay, number 3. During the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. Who were they? The alchemists, right? And what were they trying to do? Right, they were trying to turn common substances into gold. Okay, they were trying to get rich through chemistry. All right, question number 4. In the late 1700s, a man used the data from many experiments on matter to develop an idea on the structure of matter. Who was he? John Dalton. Okay, his atomic theory had 4 points, yes? Okay, now, the 4 points quickly summarized. Okay, everything's made up of atoms. All right, we don't even need to include the indivisible part. Everything's made of atoms. Okay, second point? Right, elements of the same, or sorry, atoms of the same element are the same. Atoms of different elements are different. Okay, easy way to say it. Third point? Right, and what were the keywords? They could be combined in whole number ratios, right? Okay, so when they react and they form new things, it's always whole amounts of atoms. Right. You don't change the atoms of a substance in a chemical reaction. Okay, that's kind of the 4th point. Is you don't change the atoms, you change who their partners are, what arrangement they're in, whether they're by themselves or with something else. Okay, and that changes the appearance and properties of what you're dealing with, but it doesn't change the actual substances. Okay, the actual elements that you are dealing with. Okay. Number 5, looking at this theory now, what things do you know of that can prove some of his ideas wrong? Right. We have the technology to split the atom. Okay, we know that atoms are in nature indivisible. Okay, but with technology they are divisible. they break down. I wouldn't say it's necessarily that they're dividing, because like splitting is a rather violent, like actual cutting process. Radioactive decay is more of a very slow rate of losing a particle or two, right? Like the half-life of some of those things is several hundred or even several thousand years. It would take several thousand years for you to have half of what you had before. But yeah, to some extent it does occur in nature, but not the violent splitting part. Yeah. Okay, describe in your own words the models of the atoms discussed here. Give a brief explanation as to why each was rejected or changed. Is the reason each was rejected or changed essentially the same? We always discovered what? Something new. Something was discovered that did not fit with the original model or the previous model of the atom. We have to change our ideas when we have data that doesn't agree. All right? And that's sort of the whole process of science. We learn by changing what we think we know. All right? Is it possible that our current model will change? It's possible. Okay? I mean, we have a pretty good idea now, especially with all the quantum mechanical stuff and the Large Hadron Collider and all that, of what atoms look like. Okay? But you never know. We could discover something new. All right. So the models that we discussed, first model was solid sphere, then plum pudding, then it's kind of a hodgepodge, right? Rutherford's model, okay, and then Bohr's model, and then yeah, they're kind of combined a little bit. I mean, one's more structured orbits, the other was the offsets, and the last one, the current one, is the electron cloud model. Right. Okay. Now, if I was asking a question about those on an exam, it would not look like that question. Okay, it would not be a written response item. All right, I wouldn't waste a written response item on something like that that's just recall. I would probably show you a picture of one of the models in a multiple choice question and say, which one is this? All right, because that would be a more effective way to ask about that. Okay. All right, number 7. As our knowledge increased, we discovered the atom had smaller parts. Okay, what are the 3 parts that we went over? Okay, protons, neutrons, and electrons. Protons are positive, and where are they? In the nucleus. Okay, neutrons are neutral, and they are nucleus. Electrons are negative, and where are they? In the cloud surrounding the atom. Right. Okay, number 8. 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon. Why do you suppose this is? Right. The size of the atoms of lead are bigger. There's more stuff in a single atom of lead than there is in a single atom of carbon. So naturally, even if I had the same number of atoms, the lead's going to be heavier, right? Because every one of its atoms are considerably bigger, right? When you look at the periodic table here, you see that carbon has an atomic number of 6, okay? It has 6 protons, 12 minus 6, it's got 6 neutrons, 6 electrons. But when you look at lead, it's 82, okay? It's got 82 protons, 125 approximately. Okay, neutrons is bigger. It's much bigger. It's going to be a lot heavier. Okay, number 9. Nuclear reactors use atoms with very large nuclei, like uranium, which has 237 particles in its nucleus for fission. Okay, why wouldn't they use smaller, less dangerous atoms like lithium, which only has 7 particles? Okay. Right. Bigger target, easier to hit. Okay. What else about a bigger atom makes it easier to split? Yeah, the bigger the nucleus, the more energy is going to be released when it breaks. Okay, and what else? It's more unstable. Okay, even if you were to hit a lithium atom with a subatomic particle, it might not break. It might just bounce off. The smaller an atom, the more stable it is. That's why hydrogen is the most common substance in the universe. It's the simplest, most stable form. Okay, the bigger things get, the harder it is to hold together. That's why almost all the really big atoms are radioactive. Okay, they just naturally break down. Some of these ones that you see on the bottom of the periodic table here, okay, like ununium, or however you say it, okay, they're synthetic. They've only been produced in like the Hadron Collider and things like that. Like in experiments, they break down very, very quickly. Most of them don't last more than a couple of seconds. All right, so the bigger they get, the less stable they are. Okay. atoms are indivisible. Okay, we already kind of talked about that one. That statement was believed for so long because there wasn't any technology to prove otherwise. No one was able to split the atom. All right. Okay, so from what you know of the structure of the atom, why do you think the atom stays intact? Why don't the electrons fly off? Right, there's a kind of a force there, a force of attraction between positively charged and negatively charged things. There's an electromagnetic attraction that essentially holds the atom together, along with some other sort of subatomic forces, strong molecular force, and things like that that we don't talk about in Science 10. To some extent, there is a force of there are some of those in the nuclear forces that essentially hold the protons and the neutrons together because they're so big. There are these, like I said, like the strong nuclear force and things like that that we don't talk about that hold the nucleus together, but the electrons don't fly off because they're attracted to the positive nucleus. Okay. And then number 12, same principle, it makes glow-in-the-dark materials work, is used by plants to produce food. Okay, we talked about that right at the end. Okay, sun hits the leaves. Right, so if they get excited, they gain energy, they move up. Okay, and then when the energy is gone that's holding them there, they slowly fall down the ladder, releasing their energy, and that energy can be used by other parts of the cell or whatever to harness and make energy, make sugar. All right, so there you go. Got them all. Tomorrow, guys, we will go over some stuff to do with isotopes. It's one of the few lessons that you guys do that's different. Okay, the regular Science 10s will be starting naming tomorrow. Okay.